Hi everyone, I'm excited to introduce our final project application called the Weather App, developed as part of the ITS 706 course. First and foremost, I want to extend my gratitude to my team, Cynthia, Jennifer, and Ramil, for their hard work and dedication in making this project a reality. Through this project, we have implemented numerous concepts learned in the Data Engineering Systems class, including but not limited to the CI/CD pipelines, database interactions, API integrations, and the use of the cloud services. Let me briefly outline the architecture of the weather application for you. The user interface is built using the Streamlit, and the application is deployed on the AWS services, with all deployments processed fully automated using the GitHub Actions. Additionally, API connections to the weather service and the database ensure the application functionality and responsiveness. For detailed information about the data infrastructure, I will now hand it over to Ramil to explain further.
Thank you, Javidam. I'm going to discuss the data infrastructure of our application, which is essential for ensuring its functionality. To begin with, we utilize two distinct data sets to fulfill all the application data requirements. The first dataset provides city location information, as you can see on the screen, which enables a map to pinpoint a city's location and identify its name and state based on specific coordinates. This dataset is sourced from Kaggle and contains data for numerous cities. Therefore, we processed it to include a new column indicating the weather as cities under consideration in our application. This processing is carried out using process row city CSV, as you can see here in libpy. So we activated these cities to include them in the map. As you can see here, list of cities. In addition, the second dataset includes interesting facts about various cities. This file. Unlike the first dataset, this one is synthetically generated to meet our specific requirements. And all CSV files are stored in the data CSV directory, which is organized into a row and processed subfolders to enhance clarity and ease of access. Moreover, we selected SQLite as our database due to its lightweight design and fast performance, which make it particularly suitable for efficiently handling localized application data. The database file is stored under the application DB here, as you can see on the screen. And to ensure seamless data access, we implemented specific table schemes. These schemes are detailed in the diagram available in the image folder. You can see here. It's visible from the files that the connection between the two tables is ensured by the joint use of these names and of cities and states. Finally, turning to the database API, it acts as a bridge between the application and SQLite database, encapsulating all interactions to maintain consistency and efficiency. It simplifies key tasks such as initializing a new database, retrieving data, and uploading CSV files into the database. Notably, all interactions between the database and the application occur through the database API, which is implemented in the source folder and under the dbpy file. You can see here. Thank you for your attention. Now I pass the discussion to Jennifer. Jennifer, please proceed.
Thanks, Ramil, for your sharing of data processing and the database. Hello, everyone. I'm Jennifer. Let me introduce our Weather API. The main purpose of our project is to get real-time and forecasted weather information for a city. So we need to connect our application with an API. In our case, we used Open Weather API. Here is our how our weather API works. First, we define getCurrentWeather function to fetch the latest weather information for a specific city, such as temperature, humidity, etc. Next, we created getForecast function to get weather forecast for up to 5 days. Here, we applied some statistical analysis such as average, maximum calculation, etc. This is our introduction for Weather API. I'll pass to Jovidan to talk about our Streamlit application and microservice. Thanks.
Thank you, Jennifer, for the explanation. To run the application locally, user can use the command streamlit run main.py. However, for this demo, we'll showcase the cloud deployed version of this application. As mentioned earlier, Streamlit serves as the main interface for the application. The canvas divided into two parts: sidebar, which displays the weather information, and a map, where the user can click on the city to retrieve the weather details. Initially, sidebars appears empty because no city has been selected yet in the map. By integrating our database and the weather APIs, we ensure seamless access to the real-time and the forecast data. Within Streamlit, we optimize these services for the efficiency. So let's click the relay to see it in action. As you can see, detailed real-time weather information for relay appears on the sidebar, including the graph displaying the 5-day forecast. At the bottom of the page, additional information about the selected city shown. For this case, Relay is known as the City of Oaks for its main oak trees. Relay is also home to the North Carolina Museum of the Natural Science. Currently, the application is limited to the 20 cities for visualization purposes, but it can be easily expanded to include much larger number of locations. Now I'll pass back to Jennifer, who will explain the performance metrics of the weather app.
Thanks, Jovidan, for your sharing. Hi, everyone. Since we've built the application, before deployment, we'd better do a load testing to ensure our application can work even under heavy load. Our target is to handle 10,000 requests per second. We used Loadcast to do this load testing. Here is our script. In this script, we mainly created two functions: test weather API and test forecast API to access these two endpoints. After running this script, we will go to Loadcast website where we can set parameters such as number of users, running time, etc. We set the number of users to be 10,000. Here is our running result. We can see that our system's RPS peaked around 2,000, and the failure rate is 0. Its response time is also maintained stable throughout the test. The reason why our RPS does not meet our target 10,000 is because we used the free pricing tier of Open Weather API, and this version limits our daily cost up to 2,000. However, as the testing result shows, our system can perform reliably and stably even under heavy load. This is our introduction for load testing. Now I will pass to Cynthia to introduce the deployment IAC.
Thank you, Jennifer, to help us learn about the load testing. So now let me to go over the deployment and the IAC process. In this project, we create an automated and reliable workflow to develop, containerize, and deploy our weather applications by leveraging the tools like the Docker, GitHub Action for CI/CD, and the AWS for the IAC. We ensure the consistencies, efficiencies, and scalability from development to productions. We start by creating a reproducible development environment using the Docker file in the dev container. This allows us to seamlessly collaborate in a GitHub codebase with a pre-configured setup. For productions, we use a dedicated app Docker files to containerize the applications. This file packages the application into a Docker image, optimizes for deployment across various environments. To streamline the process, we implement a CI/CD pipeline using the GitHub Actions. We formatting, linking, and automating the testing to ensure the code meet the high quality standard. The application was built into a Docker image and pushed to the Amazon ECR. As you can see in the screen, this is our image in the ECR. And this pipeline then connect to the EC2 instance, put the Docker image from the ECR, and run the application into the containers. We automate the deployment process using the IAC. The Docker was installed and configured on the EC2 instance to manage the container. The AWS credentials was security set up, enable the EC2 instance to automate things with the ECR and put the application image. Finally, the Docker container was launched within the necessary environment variables like the API keys to ensure the property functionality. As you can see in the screen, this is about our successful deployment in the EC2. In summary, this project demonstrates how the automations and infrastructure as code can simplify the complex deployment workflow. By integrating the Dockers, GitHub Actions, and the AWS servers, we create an efficiency and reliable pipeline, ensure the seamless transition from the development to production. This is all about our final project for the data engineer. Thank you for your listening.